seen in ages.
Hi, Doug. How are you? So excited.
Good to see you. I guess you're doing one of these a little bit later in the term. Does that mean I can watch yours?
I think next week. Is that right?
Yep.
Yeah.
All right. Eduardo, will you send me the link?
Oh, yeah.
Okay.
Wait, you haven't been going to all these?
No, I just learned about it. This is my first try.
Oh, they're fantastic. They're just amazing series.
Cool.
Yeah. Yeah. Still got snow?
It was
We're
really
live,
nice
right?
and warm with all the meadowlarks singing, and then it snowed last night. So yes, I had to scrape the windshields and we've got snow again. It's that time of year when it goes back and forth. So
We just got a cottage in northern Michigan, so we're looking forward to some snow.
cool.
No.
Silence.
Hi, Mike Ryan.
Hey, how are you, Joan?
Good.
Good to see you.
Yeah, great to see you.
Good morning, everyone. It's 11 a.m. in New York, and whatever time it is where you are, please, if you can mute yourself. I know I should know how to do that for everyone, but you'll help me. So there's something less that I need to do, and I'm not good at multitasking. Well, my pleasure to introduce today Doug Emlen. I will say a few words about him in a second, but before we get started, just a couple of announcements. The first one is that Doug needs to go teaching at 1. So the question and answer session, we let him go at 12:45 so that you can plan accordingly. And I think, looking at my notes, that's the only kind of administrative announcement I have. Well, since Joan was just talking, let me mention it now that Joan Strassman will be our speaker next week. So we look forward to seeing you all as well. With regards to today's presentation, it is really very, very exciting to be introducing Doug Emlen, our speaker today. We're up for a somewhat different presentation. I think he has a little bit of a surprise for us, and I am sure you'll love it. Doug is a professor in the Division of Biology at the University of Montana in the USA. He completed his BA in Cornell University, then went to do his PhD at Princeton University, both in the US, and then completed postdoctoral fellowships at Duke University. And from the postdocs went on to Montana, where he's been ever since. And he has really accomplished an extremely yes, absolutely. It's an extremely unusual, balanced approach to doing both hardcore science that has been rewarded in a number of ways that I'll describe briefly, together with impressive, rather unique science communication that I don't think we have many among us that can really get any close to what Doug has accomplished in the realm of science communication. Regarding his science, I was going over the CV. That's what we do when we need to refresh the accomplishments of our colleagues. I mean, Doug has had uninterrupted NSF grants ever since he started. I think I counted 5 or 6, and I mean the 3-4 year full grants, not the DDIGs and all those that we may include in the CVs as fillers. What else did I really notice, which is remarkable? Of course, I mean, no shortage of publications, no shortage of all the things that we do at his stage in the career. But then going on to the science communication, he's done an awful lot. I mean, he's published this book with Carl Zimmer. The title is Evolution, Making Sense of Life, which is a fantastic textbook. I mean, it's the one that I really keep close to my desk if I ever need to go kind of clear my head on some basic topic on evolution. And he's just published, for those of you who are joining us now, let me share my screen again. He's just published, a little bit out of luck, this book that he was telling us came out right before the pandemic, Beetle, One Scientist's Journey of Adventure and Discovery. So he wasn't very lucky with the timing for the book coming out. I strongly recommend you check it because I have no doubts that with the engagement with which Doug writes, I'm sure you will not be able to put it down. But he wasn't lucky, and it came out at a time when presses were struggling and nobody was really thinking of purchasing books. We were all trying to buy toilet paper and the like. So with that, I think that I will stop, and I will stop by saying, very well then, Mr. Emlen, sir. Let's have a little talk about beetle battles.
Thank you.
So Doug, let me make you host.
I want to add one other caveat because
Yes.
I'm also, true confessions, I'm going to try and experiment today. We've all had sort of an extraordinary year in our own ways, and we've all had to learn how to teach in a pandemic, which has been quite the experience. And I guess I want to add one caveat that I'm trying to teach a 200 student class right now in genetics and evolution and find ways to reach these students and keep it engaging. And it's been tough. And trying to stand up with a podium and my notes and give a lecture live on Zoom. I can't see the camera. I can't see which students are tuned in. I can't see the chat room. As soon as I go to the screen, all they see are the slides. They lose being able to see me. I finally tried something radical, and I went into a studio and I started pre-recording my lectures in advance with a much better camera, much better lighting, better audio. And then assembling the lectures in a program called Camtasia so that I can transition between the slides and have both there at the same time. And now what happens is the students tune in live and I play the lecture, but I'm right there and I run the chat room, and it's turned out to be brilliant. I mean, I think the students really appreciate the improved quality of the presentations, and the discussions and the questions I'm getting in the chat are way better than I would normally get with a live lecture, because people are much more comfortable bouncing stuff around and it doesn't slow everybody else down. So actually, at their suggestion, I went out on a tangent and I recorded this talk. So I did it just for you. This is the first time I've done it. The students think this is a much better way to go. And it means I'm going to hit play and I'll be sitting right here running the chat. My wife, who's also a biologist, thinks it's going to be a disaster, that nobody wants to have a seminar speaker give a live talk that's pre-recorded. So I don't know how it's going to work, but I put 7 hours into recording and building this thing. So I kind of hope you like it. And I'd like to give it a shot and see. The other thing, there's a few people, like I see Dan on here, that have heard me talk about some of these ideas before. I'm doing something a little bit different today. I ran it by the coordinators to make sure it was okay, but I'm going to throw some crazy ideas at you that are thought-provoking, that are controversial, and are sort of outside of my main research area, because I think they're timely and I think they provide an important example of the relevance, if you will, of basic research, in particular, the kinds of basic behavior evolution research that we all do, but in an arena or a context is totally unusual. So anyway, if that works, let's give this a try.
Doug,
Please be honest. If you don't like it, let me know. Yes.
Doug, so that people know, you said that you anticipate the recording is going to be 47 minutes, right?
Yes.
So we'll be fine. If those of you who need to go at noon, the presentation will finish before then.
Okay, you ready? Let's do this. Thank you. So as you just heard, I'm an evolutionary biologist, and I study the development and evolution of animal weapons. Specifically, in my case, this means the horns of beetles. And over the years, my students and my colleagues and I have used a variety of different approaches to study these weapons. So for example, we've used biomechanics and engineering approaches to look at how beetle horns function as tools that lift or pry or twist an opponent off the side of a tree. And we've used genomic and developmental genetic approaches to study how these weapons grow. So to try to look at the genes and the developmental pathways that build a horn and control how large that horn grows to be. And we use population genetics to reconstruct how these weapons have evolved, so changed in size or shape over time. So both from population to population and from species to species. We even spend long nights out in the rain watching these beetles, and honestly by we, I mean my graduate students, to see how these beetles fight, to see how they're using the horns, and to measure the strength of selection acting on these horns in natural populations. And our latest twist, incidentally, is that we've discovered that females are much more choosy than we would think for a species with huge weapons like this. And even after battling to hold on to a territory on the side of a tree, these males still have to turn around and court the females who approach, including a variety of types of song, so 3 different types of stridulatory song, and trembling dances, and we think a complex blend of smells made up of cuticular hydrocarbons. Right now, we have soundproof boxes set up in the lab, and we're trying to record these courtship sequences so we can begin to tease apart what kind of information is contained in these signals and what specifically the females are preferring. But I'm not going to talk to you about any of that today. I mention it sort of fast and up front so that you know where I come from. Instead, I want to share a wild set of ideas with you that I think are even more exciting and certainly more important. A few years ago, I had a chance to step back from the beetles, to pore through the literature on all sorts of animal extremes. Crab claws, walrus tusks, fly antlers, elk antlers, the works. The weapons in all of these species are so outlandish in proportion that they look like they shouldn't be possible. The animals that wield these things look like they should tip over or trip or collapse under the bulk and the weight of these weapons. Well, I compiled everything I could on all of these crazy and wonderful weapon extremes to ask basic questions like, how did their weapons get to be so big? And is there such a thing as too big? I also scoured the literature on another type of weapon extreme, our own. For as you all know, we humans make weapons too. Manufactured weapons aren't parts of our bodies like tusks or horns, and instructions for their construction aren't encoded in DNA. But their forms change over time in much the same way as animal weapons, and the directions of this evolution are molded by similar forces of selection. Successful models are copied and spread, while less successful ones gradually disappear, so that populations, if you will, of manufactured weapons transform through time. And when the conditions are just right, these weapons can get taken to extremes too, surging forward to bigger and bigger sizes, deadlier, faster, and vastly more expensive. So I laid side by side the literatures on animal and military weapons to look at how and why weapons get big. And wow, am I glad that I did this, because the parallels that I found literally rocked my world, utterly transforming the way that I looked at extreme weapons, changing in many ways how I looked at my own system, the beetles, and even to a startling degree, changing how I looked at the political realities of the world around us, things like terrorism and weapons of mass destruction and national security. Extreme weapons, I'm going to suggest to you, are extreme weapons. Animal, human, it does not matter because their stories are exactly the same. Well, with the time that I have today, I want to show you what I mean by highlighting 3 of these parallels between animal and military weapons. And the first of these begins with a problem. It's a big problem. I mean, arguably, it is the overarching question for all of these animal weapon systems, at least. Why do only some species have big weapons? I mean, the quick answer is simply that weapons in these particular species got caught up in an arms race. So swept into a cycle where bigger was better, a lot better, so that weapon sizes ratcheted up fast, culminating in species where animals wield these extraordinary structures. But that just reframes the question. Why did arms races get triggered in these species and not in so many others? This may look like a lot of species, but I assure you it is not. Considered against the backdrop of the diversity of life, it's a pittance. It's a drop in the bucket. It's less than 0.1% of described animal species. So what's so special about these particular species? How can we explain why they have such huge weapons when so many other species, even closely related, otherwise biologically similar species, do not? So is there a generalizable set of conditions that precipitate arms races in animals? And can an appreciation of these conditions help us explain this sort of big picture pattern of morphological diversity? Well, it was clear right away that 2 of the central tenets of animal behavior held sway here. And together, they helped explain a lot of this diversity. So first, there was no question that the biggest animal weapons were all the product of sexual selection. So one quick aside here, there is one other ecological context that also sometimes leads to the evolution of huge weapons. A specialized style of hunting, ambush predation, can also drive the evolution of giant claspers or jaws in some predators. And I can talk more about this other context if you like after the talk. But most of the time, extreme weapons evolve in the context of sexual selection. Intense competition among males for access to females was a driver of weapon evolution in the overwhelming majority of these species. I can explain the logic of sexual selection, including why it is almost always males battling with rival males and not the other way around, after the talk if you like. Suffice this to say that the backdrop for all of these weapons was males battling with rival males over access to females. Intense competition was, in a sense, the first critical ingredient for these animal arms races. The second key ingredient, also a fundamental tenet of animal behavior, concerns the economic defensibility of critical or limiting resources. You're all almost certainly familiar with the military equivalent of this. Some locations, by virtue of their restricted access, are more readily defended than others. So surrounding things with high walls that open to the outside only through sort of sturdy gatehouses or narrow restricted tunnels that serve as choke points, this can make them much more cost-effective to defend, acting as force multipliers. And you're probably just as familiar with the cybersecurity equivalent of this, where firewalls restrict access to a small number of heavily protected gateways or tunnels. And I love this artist's rendition of a VPN tunnel, by the way. Well, this logic applies to animals too. And all else being equal, resources that are clumped or otherwise restricted access, so resources that have smaller attack surfaces, are more likely to be cost-effective to defend than are resources that are more uniformly distributed across the landscape. This is the essence of resource defense mating systems in animals, and together with intense competition, these two ecological principles go a long way towards explaining why some species have big weapons and why so many others do not. I love these ideas. They're not wrong. They're in all the textbooks. I've been teaching them in my classes for 20 years. The problem is they're not enough. There's still a piece missing. There has to be, because lots of species have intense competition and limiting or localized resources, but they don't have big weapons. I'd see this all the time when I worked with dung beetles. I could be in a Panamanian rainforest looking for howler monkey dung, or in a pasture in North Carolina, or in Yucca, Australia, or looking at elephant dung. It didn't matter, because in all of these environments and all of these places I would find side by side species with and species without big horns. Ecologically, these are very similar species. Same habitats, same seasons, even sometimes literally the same piles of dung. But only about half of these species invested in big weapons. Well, they all face intense battles for access to females, and they all guarded localized or limiting resources, either females located inside tunnels or little balls of dung. But only the species that fought inside tunnels ever had the horns. I used to explain this by pointing out that tunnels restrict access to key resources, making them cost-effective to defend, exactly as theory predicted. But honestly, little balls of dung with females clinging to them, those are pretty localized and defensible too. So what else was different? Well, this question haunted me for years, since the pattern was so striking, yet their overall ecologies and life histories were otherwise so similar. Eventually, I started looking at the details of the fights themselves, and I started looking across more and more species and more types of weapon systems. Clearly, some fights are won by traits other than big weapons. So swirling acrobatic midair snarls, for example, of birds and butterflies and wasps spring to mind, where stamina and agility are likely to matter most, and where clunky, costly weapons would only slow you down. But there was one more key ingredient, something that I'd never thought of. Something that, as far as I can tell, nobody in animal behavior or biology had ever thought of. Duels. It turns out that the fights must play out as one-on-one duels rather than multiplayer scrambles. The epiphany for me came from the military literature. As I've already alluded, there's a rich and vast literature out there on technological innovations and the evolution of manufactured weapons. And some very smart historians have thought a great deal about when and why arms races occur. And they've done it without any biology at all. Evolution, animal behavior, or otherwise. So they bring a fresh perspective to these topics. And in this case, the missing piece to the puzzle came from the writings of a rather eclectic aeronautical and automotive engineer, who around the time of the First World War set out to model battles of attrition. I don't have time to go into the details of his models, but the essence of his logic was this. If opponents can concentrate their fire, so if they can attack all at the same time, then given a choice between spending more of your resources on bigger or better weapons or additional training for your existing troops on the one hand, or simply adding more troops on the other hand, it always pays to add more soldiers. Do not invest in expensive weapons and instead just get more soldiers. Well, Lanchester's laws are thought to have launched the soon thriving industry of operations research. And one of the lasting legacies of his work is the maxim of never divide your forces on the field of battle. But it was the other half of Lanchester's logic that got me excited. Turning his logic around, his models suggested that when soldiers do not concentrate their fire, when they line up toe-to-toe and they confront each other one-on-one, then it often does pay to invest in bigger or better weapons. Because when the fights play out as duels, the better fighter wins. It's no accident that for 5,000 years of recorded human history, in just about every culture, the only type of fight that has ever mattered for honor or status was the duel. Ritualized, repeatable, and fair. When rivals face each other in battle one-on-one in contests of strength, the better fighter wins. And this often means the contestants with the biggest, the best, or the most expensive weapons. Duels, military history suggested, could create situations where bigger weapons performed better than smaller ones. Duels could precipitate an arms race. Well, what about in animals? Well, this is the fun part because I now think that duels matter for animal battles too. Fights that play out as duels are predictable, often escalating into protracted, even ritualized contests of strength, where the bigger or the stronger male, the male with the biggest weapons, is likely to win. Contrast this with scrambles, where lots of rival males all tumble simultaneously into the fray. The outcomes of multi-attacker scrambles are far less predictable. In fact, they're often wildly chaotic. In scrambles, the better fighter might not win, and costly big weapons are far less likely to be worth their price. So I now suspect that duels are the final piece to the puzzle, the third critical ingredient for precipitating animal arms races. And for the next few minutes, I want to take this idea for a spin. Because it turns out there's some very predictable ecological situations, sort of backdrops for the battle, if you will, that by their nature cause animal contests to play out as duels. And these situations, I suspect, act like cauldrons, facilitating the rapid evolution of big weapons. And the first of these is tunnels. Sure, tunnels restrict access to a resource, making it economically defensible. But they also align male contestants so that they necessarily confront each other face to face and one-on-one. 10 rivals can't attack all at once because only one of them can fit into the tunnel at a time. I've already told you that for the dung beetles, the biggest difference between the species with and the species without weapons was tunnels. Ball rolling species which I'll note fight above ground in the open in mad scrambles that often involve multiplayer attackers, ball rolling species never ever have big weapons. Tunnelers, who fight face to face inside these tunnels underground, very often do. In fact, lots of species with big weapons fight over tunnels. Shrimp and crabs fight over burrows, and very often these species have huge weapons. Fiddler crabs are a great example of this. Wasps with long tusks, big-headed, big-mandibled bees, tusked wettas, even fanged frogs. All of these species fight inside burrows or tunnels. There was even a giant horned rodent, now extinct, that lived in Montana that appears to have fought over burrows. In species after species, the constricted space of a tunnel aligned male contests so that they necessarily occurred as duels. And that final ingredient appears to have triggered an arms race. Branches work the same way, incidentally. I mean, in a sense, they're just inverse tunnels, since a branch, like a tunnel, is a linear substrate that can be blocked, and along which a rival must pass. I always like to picture Indiana Jones or Gandalf guarding a bridge. It's exactly the same idea here. While many species of rhinoceros beetles fight over branches, as do leaf-footed bugs, even horned chameleons fight over branches. There he goes. And all of these species have huge weapons. Stalk-eyed flies illustrate this particularly well. These amazing flies live in the old world tropics, and they roost at night on these sort of dangling rootlets that hang down like threads from the undersides of tree trunks in these small tropical streams. Males fight to guard these hanging threads, if you will, and females collect on these roosts each night and mate with the male on that thread before they leave the next morning. So males battle over possession of these hanging threads, and just as in tunnels, the linear substrate of these threads aligns male contests so that they necessarily play out face to face as a successive series of duels. And the fights are predictable, and selection favors males with the biggest eye stalks, leading in some cases to these ridiculous extremes. And where there are species that break these rules, so there are 5 species of stalk-eyed fly that, for example, no longer roost on these hanging rootlets. The prerequisites fall apart, and all of these species have since lost their exaggerated or their extreme eye stalks. And there are many species that fight over resources that are very localized, so small in a sense that a male can literally stand over the resource to guard, swiveling as you would to face an opponent that approaches. I like to think of this like an ice fisherman fighting to hold on to the hole that he's drilled into the ice. These species don't have tunnels or branches to force an alignment of the contestants. But because males sort of stand over the resource, and because they can swivel to face each opponent as they arrive, these fights also very often play out as a succession of duels, with rivals challenging each other face to face and one-on-one. Many of these species also have huge weapons. The species of rhinoceros beetle that we study does this. So for example, females collect to feed on wounds on the side of the tree that ooze sap, and males have to battle with each other to be able to stand guard, to stand over that resource and mate with the females when they arrive. And this video was made by one of my graduate students, incidentally. The antlered flies do this. So they stand guard over tiny holes that have been drilled into the bark of a fallen log or a fallen tree. Females need these holes in order to lay their eggs, and males that are able to hold their position, to stand their ground over these holes, are able to mate with the females when they come through. Stag beetles fight to guard wounds, so like the rhino beetles, sap oozes on the sides of trees where the females visit to feed, and males battle with rivals to hold on to those territories, and the biggest males with the largest weapons win. And here too, as soon as one of these preconditions breaks down, so there's one species of stag beetle where the females no longer collect at these sap oozes, as soon as one of these preconditions breaks down, they lose the extreme weapons. And one of the most extraordinary of all animals, the harlequin beetles, with literally a 16-inch reach from the tip of one foreleg to the tip of the other. They use their gangly legs to grapple face to face over wounds on the sides of fallen fig trees. And here again, males face each other one-on-one in a succession of duels. Finally, there are lots of species that fight out in the open that still end up confronting each other in duels. Here, I think it's the nature of the fight itself that results in the duel. Males in these species use their weapons as signals, as deterrents, sizing each other up and only escalating the contests in stages. These fights ratchet up the danger in steps, escalating all the way only when rival males are very evenly matched. Fights like this don't happen by accident or by surprise. They escalate slowly and predictably, and by the time they get dangerous, they are always one-on-one. So even out in the open, their fights fulfill that last crucial prerequisite of unfolding in duels rather than scrambles. So what I'm proposing here is that we now have a generalizable explanation for when, where, and why particular species evolve extreme weapons. When species meet these conditions, selection very often favors the males with the biggest weapons, sort of pushing their evolution to the extreme. The missing ingredient for explaining animal arms races was duels. Simple changes in behavior. So fighting inside tunnels, for example, or on branches instead of out in the open, caused males to begin to confront each other one-on-one in contests of strength rather than in scrambles. And this simple change in behavior precipitated an arms race, triggering explosive evolution of bigger and bigger and bigger weapons. Well, we see exactly the same thing when we look to our own military past. This shouldn't surprise you. I mean, after all, that's where the idea came from. In these cases, it is usually a change in technology that alters the way that opponents interact, causing them to confront each other one-on-one in duels rather than in scrambles. And in case after case, this simple change in behavior from a scramble to a duel tipped the balance of selection, sparking an arms race. And I'll show you what I mean with a few examples. For almost 1,000 years, oared galleys shuttled troops from place to place in the ancient Mediterranean, with almost no change at all in ship design or ship size. Then, someone invented the battering ram, a cast bronze protrusion jutting from the front of the boat. This simple change in technology changed everything. Boats stopped being vessels of transport and started being units, weapons in and of themselves. Ships could strike other ships and sink them if they were fast enough. So ships started to line up against rival ships in one-on-one engagements or duels. And that simple switch in behavior precipitated an arms race. For the faster ship had the advantage, and faster in that age meant more rowers. So ships started getting longer and longer and longer until their hulls started to buckle. So they started stacking rowers on top of each other, and one row of oars became two, and then two rows of oars became three. Soon shipbuilders were adding 2 or 3 men to each of the oars, so 3s became 4s, and then 5s. Soon there were 8s, and then 9s, 11s, 13s. Ships got bigger and bigger and bigger until the race climaxed with a monstrosity called Ptolemy's 40. After 1,000 years of stasis, one simple change in technology aligned ship interactions so that scrambles became duels. And from that point forward, the race was on. In just 300 years, warships surged from pentaconters oared by 50 men to massive double-hulled behemoths powered by 4,000. Flash forward another 2,000 years, give or take, and we see the whole thing happen again. By this point, ships had bigger hulls, and all power was by sail. Sailing ships didn't make very good battleships. They didn't ram very well. They tried, but the rigging would get all tangled up, and it's not very easy to back up with a sailing ship. Attempts to mount cannon on the decks of these ships failed because that much weight up high made these ships tippy and unstable in rough seas. But the invention of the closable gun ports changed the rules of engagement. Now cannon could be moved lower, down close to the waterline, where their weight actually made the ships more stable. and you could pack a lot of them in along the length of each side. But these guns were not accurate, and on rolling ships and open seas, they were only effective at very close range. So ships had to line up side by side with another ship in order to fire their broadside. Voila, one-on-one engagements, duels. And from that point forward, bigger was better. Bigger ships could pack more cannon, and bigger cannon, they could unleash the bigger broadside. So one row of cannon became two rows of cannon became 3, 6-pounders gave way to 7-pounders, then 8-pounders, 22-pounders, 30-pounders, more cannon, bigger cannon, the race was on. Here too, the critical trigger of the arms race was a change in behavior, a new technology that forced battles to be fought at close range and one-on-one, so the nautical equivalent of a tunnel or a branch. And from that point forward, bigger became better, and selection pushed these ships to the extreme. Well, when you stop to think about it, this simple prerequisite applies to lots of history's greatest arms races. One-on-one fights, both in battle and especially in tournaments, sparked explosive evolution of arms and armor in medieval knights. And one-on-one dogfights among the very first military aircraft sparked an arms race in fighter design in planes. Again and again and again, the same prerequisites trigger the arms race. Okay, so the first big parallel is duels. A certain type of fight, one-on-one encounters, helps precipitate arms races in both animal and military weapons. Well, it turns out that once started, both animal and military arms races unfold in the same way. So they proceed through the same sequence of stages, if you will. And one of these stages is deterrence. As these weapons get big, they begin to function as signals in addition to actual tools of battle. Only the best conditioned males, the absolute top of the lot, with the largest body sizes, the best immune systems, the most stored nutrients and energy resources, only the best of the best can produce the really, really big weapons. And that means that weapon size becomes a pretty good indicator, a billboard, if you will, of the fighting ability of a male. And rivals start to use weapon size to decide whether or not to escalate a fight. They don't just lunge into battle, they assess each other beforehand. Whose weapon is bigger? Because weapons are honest signals of fighting ability, it often pays the smaller male to walk away. Weapons start to act as deterrents, settling contests without dangerous battle. And in fact, in species with the biggest weapons of all, the vast majority of contests get settled this way. One study of caribou, for example, watched more than 11,000 male contests. Only 6 escalated all the way to full battle. 6 out of 11,000. Caribou have the largest weapons relative to their body size of any living vertebrate, and more than 99% of their contests are being settled without a fight. This leads to an odd paradox, that the species with the biggest weapons are often the most peaceful. I mean, make no mistake, they can and they definitely do fight. But full-on fights tend to be relatively rare, and the net effect on these populations is peace. Well, we use big weapons as deterrents too. During the heyday of the British Empire, for example, first-rate ships of the line were absolutely state-of-the-art weapons, and they made splendid deterrents. Simply sailing one of these ships into troubled waters could settle disputes on the spot. The wooden hull of one of these ships required 8,000 oak trees that were 100 years old each. And for European nations that were largely deforested already, that cost was prohibitive. Most nations had none of these ships at all, and Britain had dozens and dozens in her fleet. And this period was called, incidentally, the Pax Britannica, or the British Peace. Well, the United States uses its most expensive ships the same way today. A Nimitz-class carrier and its associated strike group costs more than $20 billion. The United States has 11 of these carrier strike groups. No other nation has even one. China's working on their first, but at the moment, no other nation has even one. Massive, powerful, prohibitively expensive, our carriers function both as weapons and as deterrents. Portable projections of military power shuttled like chess pieces to stabilize troubled regions or to implement foreign policy. And I'm telling you that these weapons at their core are no different than these. Extreme weapons are extreme weapons, and their biology really is the same. I also have to point out that all of this logic applies at the level of political landscapes and nation states too. So the Cold War, for example, the most terrifying arms race of all time, was at its core a duel, as the world stage coalesced around two opposing superpowers. And deterrence played a big part in that arms race too. In fact, it may even be the reason that we're still here. Okay, now for the last and arguably the best parallel here. So you're stuck in an arms race, and weapons are surging forward, evolving to bigger and bigger and bigger sizes, more elaborate, more extravagant, and much more expensive. Well, we've just seen that this makes them great deterrents. Billboards honestly advertising the fighting ability of an opponent. They work as deterrents because only the best of the best, the richest nations or the biggest and healthiest bulls and bucks, only the wealthy can afford to pay these extraordinary costs. So what does everybody else do? Suppose you're not the biggest male on the block. You're smaller and weaker. Life didn't shine on you the way it did on them. What do you do if you can't afford the biggest and the best weapons? The answer is you cheat. It turns out that cheating is rampant, and once you start to look for it, you find it everywhere. So take dung beetles, for example. The biggest and the best males, these are the males that have the long horns. They win the fights, and they guard the entrances to the tunnels containing the females. Well, not all males are big. In fact, most of them are pretty tiny. And tiny males don't play by the rules. So for one thing, they ditch the big weapons. Horns are expensive, and they're not going to help you anyway if you're small. So these males are hornless, and they actually look and act a lot like females. And they sneak into tunnels on the sly. Instead of fighting a losing battle at the entrance, they dig their own tunnel, a side tunnel, and in this way they can slip into a guarded tunnel beneath the guarding male. And when they do, they go straight down the tunnel, find the female, mate with the female, and turn around and leave. They can be in and out of these tunnels in less than 10 minutes flat. So as you no doubt know, sneakers like this lurk in all kinds of animal populations. So just to give you a couple of my favorites, sneaky small cuttlefish cloak themselves in colors that look like females, and they can sidle right up to a courting male, literally slipping in between the male and the female he's courting. Sneaky male salmon zip into a territory, raining sperm down in a cloud over a female's eggs, in and out of the territory so fast that the guarding male can't stop him. And sneaky bighorn sheep, called coursers, race into a big bull's territory and attempt to mate with females on the sly while he's distracted in the middle of a battle. In species after species after species, males who can't afford to play by the rules break the rules and cheat. Well, cheaters affect the whole dynamic of the arms race because they steal reproductive success from the big weaponed males. Those males still pay the full price of building and using their weapons, so the cost to them stays the same. But now the payoffs, the benefits that they glean from having those weapons get smaller. Eggs that are fertilized by sneaker males aren't fertilized by the guarding males. He produces the horns, he fights to guard the tunnel, but the offspring of that tunnel gets sired by another male. Well, as long as these sneaky males steal only a little bit, not much changes. The benefits of big weapons stay huge and the arms races surge forward. But when cheaters start doing too well, then they can collapse an arms race. I mean, suddenly it's not worth it anymore to produce the really big weapons. Males without the big weapons start doing better than the males with them. And we expect these big weapons to quickly disappear. Well, cheaters erode the success of our biggest weapons too, and they've done so for thousands of years. Asymmetric warfare, guerrilla tactics, are the classic cheat. If you don't have the resources to face an invading force head on in conventional battle, then don't. Guerrilla tactics are exactly like sneaky male fish and beetles. They never wear military uniforms. Instead, they hide, blending in with civilians in much the same way that sneaky males look and act like females. And they use makeshift, inexpensive weapons like Molotov cocktails, pipe bombs, and IEDs. Here too, as with animals, as long as they don't inflict that much damage, nothing changes. State-of-the-art weapons continue to be well worth their price. But when a cheating tactic starts doing too well, then overnight it can collapse an arms race. And over throughout history, technologies that cheated have collapsed an arms race. Often, these involve a new type of weapon. Always, they involve a tactic that's cheap. They win by not paying the price of these huge weapons and by rendering those expensive weapons obsolete. English longbows and gunpowder, for example, spelled the end for medieval armor. Once plate armor could be pierced, then suddenly it wasn't such a great idea to ride into battle sitting astride a horse like a big, shiny, bulky target. And overnight, armor went from being a fantastic form of protection to an expensive, heavy, bulky liability. Well, so too. Exploding shells shattered the arms race of sailing warships, and submarines caused ironclad battleships to be obsolete. In every case, and there are dozens, new strategies that broke the rules of engagement caused our most expensive weapons to suddenly be obsolete. Hugely expensive, but no longer worth the price. Well, as I close, I have to flash forward to the present day and to leave you with a sobering thought. Because I'm starting to suspect that we may be dangerously close to such a situation right now. As you all know, the US today stands alone as the sole superpower, and our weapons are both exorbitantly expensive and magnificent. We have the most advanced weapons in the world, and we are almost certainly safer because of it. Our newest technologies have incredible potential both as weapons and as deterrents. The Gerald Ford class aircraft carriers, brand new at just $13 billion apiece. And the F-35 Joint Strike Fighter, an aircraft that cost $400 billion to design and build. These are great examples. But all of these weapons depend critically on software. Steering and navigation of our submarines and aircraft carriers, guidance of our missile systems, and also the sensor nets that we deploy to detect incoming missiles, command and control, safeguards on our nuclear weapons. All of these are controlled by computers and software. A pilot can't even fly a modern fighter without this software. Fly-by-wire systems, as they're called, are critical for handling these planes and for making sure that the pilots don't black out from the G-forces. And all of these systems are vulnerable to hackers. Cyber hackers are the ultimate sneaks, surreptitiously worming into our control systems. I used to think that the danger of cyber hackers was a stolen credit card number or identity theft. And oh my gosh, did my worldview change when I started researching all of this. So as you may or may not know, the United States has already been hacked several times. In 2004, the Chinese broke into a suite of our state-of-the-art weapons systems in an event called Titan Rain. And in 2013, we caught them at it again. This time, they'd compromised the Terminal High Altitude Missiles Defense System, the F-35 Joint Strike Fighter, the F-22 Raptor, our MV-22 Osprey, as well as 37 other weapon systems, including our drones. And the scariest part about all of this? They weren't simply stealing secrets. They were inserting code designed to hide there, to lurk undetected. These scripts, had they not been detected, would have given the Chinese complete control over our weapon systems. By activating these hidden programs, they could have turned our most expensive weapons against us, raising the alarming question of whether our weapons too might soon be obsolete, like medieval armor and battleships before them, simply no longer worth the price. The silver lining, if you want to call it that, is that the United States military is well aware of this threat to our national security. And I had a chance to hear General Michael Hayden, former director of both the NSA and the CIA, talk at a conference on cybersecurity in Washington, D.C. in 2016. He considers cyber hacking to be threat number one. And he considers cyberspace, or the internet, to be the fourth theater of war. So land, sea, air, and now cyberspace. And he says that they know that the Chinese, the Russians, the North Koreans, as well as probably the Iranians, have buildings full of hackers working 24/7 to break into our systems. This is the new arms race, in a sense, since he admits that we have just as many on our side hacking back. And at least according to him, our hackers are better than their hackers, at least for now. I got to present at that conference too, right after General Hayden. If you can imagine me standing in front of that crowd talking about animal arms races and sneaky male dung beetles to the chief technical officers of the FBI, the CIA, the Department of Defense, NSA, as well as Microsoft, Google, Northrop Grumman, and Lockheed Martin. Talk about a fish out of water. And to show you just how strange and exciting life can be, and how far crazy ideas like this can take you, I recently got to witness these state-of-the-art technologies firsthand. The Navy was kind enough to fly me out to the USS Carl Vinson, so CVN 70, and head of our Carrier Strike Group 1, while it was at sea in the Pacific conducting operations. That meant that we had to fly out to the carrier in these transport planes and slam down on the deck and catch the tripwire, so go for an arrested landing from 150 miles an hour to 0 in like 100 yards. And we got to observe the inner workings of an aircraft carrier at sea. From the bridge to the bowels of the ship, we got to stand on the flight deck as F-18 Super Hornets and brand new F-35 strike fighters came screaming in for landing, slamming down on the deck and yanking to a stop literally 20 feet from where we stood. I mean, I took this picture with my cell phone to give you a sense of how close we were. And I got to look at the new F-35 fighters firsthand. The helmet alone on these things cost $500,000 each. And most importantly, I got to talk to the crew. From the cooks to the mechanics, the pilots, the first officer, and the captain. And I asked all of them about the threat of cyber hacking. Guess what? It's threat number one. This is what they worry about all the time. It literally keeps them awake at night. So I confess, this has been quite a journey for me, a ride more wild than I ever could have imagined. I'm a biologist after all. I study beetles, not battleships. And I used to be nervous about writing and speaking about these parallels with the military. I titled my book Animal Weapons, honestly because I was scared to go all in with the military implications. I'm not scared now. I've talked to admirals and generals, foot soldiers, sailors, historians, and the chief technical officers of the Department of Defense, the FBI, the CIA, and the NSA. These parallels are real. And I love the idea that basic muddy boots research can extend so far. I mean, who'd have thought that poking around in the mud in a rainforest, studying dung beetles, could ever tell us anything useful about our own military weapons or about national security? But I have to say that the more I dug, the more convinced and astonished I became that there really are parallels between animals and ourselves. And I know already that these parallels are transforming how I think about biology, guiding our research in new directions that we never could have anticipated. And my gut tells me that it's going to be just as useful the other way around. So for example, if you follow the United States National Defense Strategy, for the last several years, it has all coalesced around something called great power competition, which sure looks like we're setting ourselves up for yet another duel. And I think biology has a lot to tell us about how that's going to turn out. And I'll point out that this past fall, when everybody was glued to their televisions terrified about the outcome of the elections, and we were all focused on whether our democracy would hold together, Russia snuck in underneath and hacked all of our systems. They succeeded in a massive hack of our military technologies and our national infrastructure. So they essentially had us all focused one way, worried about tampering with the elections, and while we were looking one way, they gutted our systems. And we're still figuring out just how bad that particular hack was. So again, a timely reminder of how relevant some of these ideas are to things like national security. But for now, at least, I hope that I've convinced you that there are some exciting and surprising insights to be gleaned from the extraordinary weapons of beetles and crabs and caribou and elk. Thank you.
Thank you. Thank you very much, Doug. I lost you. There you are. Okay, you're back.
I'm here.
You're back. And we
I
know
got buried in the chats, by the way. There were so many discussions going that if I didn't get back to any questions, I apologize.
we
I
know
had
he
like 15 different directions. Anyway.
We know he didn't leave. So thank you very much for a definitely provocative presentation, an engaging one. And I have no doubts that we will have lots of questions and answers. One more time, in case you are new to the FINE seminar series, what we do next is for the next 45-50 minutes. One more time, Doug needs to go teach at 1. So we will finish the question and answer sessions 12:45. So what we do next, we start taking questions and answers. As I was listening to Doug, I was reflecting, I was pondering what role should I play? Usually we moderate the conversation. And so it's really walking this very thin line between moderating, making sure that the conversation stays somewhat related to the goal of the FINE seminar. But on the other hand, if there's something that I definitely don't want to do, is tell anyone what they should be saying. But I imagine that we do not want to spend the 45 minutes talking politics. And I invite you, as he was saying, China and the US, I'd rather put names of 2 species or males and females or whatever you choose. But those are just my thoughts more than. So I see, again, for those of you who are new, what we do is just please type a question mark in the chatting window, send it to everyone. That allows us to be fair because you know where you're on the list. And if we get heavy bias towards our senior colleagues, I may start mixing our senior colleagues and students. It is a goal of Lauren, Karsten, and I to really engage students and younger colleagues in the conversation. So if I skip you, it's because I may go down, take somebody from YouTube or a student, then come back to the senior colleagues who usually are less shy than our students. We need to hear from the students as well. So having said that, let me go. I see.
But I want to ask a question first before we get. I'll talk about anything. You don't have to shy away from politics. As far as I'm concerned, we need to be thinking about these difficult issues. And as a bunch of scientists, if we can't throw down on these things, then how can we expect other people to do it? So I'm happy to discuss anything. But my first question: did the recording work? Was that okay? I guess sort of some people saying it's going to be a disaster, other people saying it's the way to go. Is it worth doing this again? I'm seeing nods. Awesome. Okay, cool. Because you guys are the guinea pigs. This is the first time I've tried it with a research seminar. So
something else that I may do, and I please, this is a difficult situation to be in when there's so many questions. If you've been a regular participant, if you've already had your chance over the course of our 20-something or so talks to ask lots of questions, maybe if I see a new face, I'll give that person priority as well. I guess it's my prerogative to play a little bit the decision maker here. But we're going to get started. The first question, I hope I'm getting it right. Let me be sure if I miss somebody, then I'm not going to see you again. I think the first question comes from Sari Van Bell. Sari? Sari, are you there?
Maybe
okay,
not.
We'll come back to Sari later. So we have so many questions that, Sari, I'll come back. So the second one is from Leticia. Leticia, are you there? Okay, and so.
I scared everyone away.
Eleanor, you're next.
Oh, they're saying you have to unmute. They're trying to ask, but they're muted. I see that in the chat room now.
Okay. Allow participants, there you go. So let's go back to Sari then.
Hey. It's very annoying that you want to say something, but you're totally mute, and it's like, hey, I want to say something. So I'm Sari van Bal. I'm a postdoc at the University of Texas in Austin, and I study howler monkeys. So I was.
Oh my God, I have so many memories of howler monkeys. Sorry.
But I want
spent
to
2 years looking for howler monkeys at sunrise every single morning to find the dung, to find the beetles. So anyway, go ahead. Sorry.
I want to start off with a bit potentially an odd question. So I'm a bit nervous about it. But why is it a surprise that there is a parallel between what animals do versus what we do in terms of weapons? Isn't it? Your talk was like, duh, of course, and I don't mean in the sense.
No. Let me run with this. It's a great question. And I have two
now
people.
that you have put it together, it's more like, yeah, of course.
So first of all, I was when I did this when I was trying to research a book where I was trying to tell the stories. I wanted to use the stories of the most extreme species as a hook to try to get people that wouldn't otherwise read about these things sort of immersed in biology. And I was trying to write a book telling these stories, and my publisher and my editor kept saying, you need to look at the military stuff too. And I actually read a ton of military history on the side, just like as a hobby, but I'd never looked at it that way through the lens of a scholar. And initially I was scared. It's like, wait a minute, I'm a biologist. It's okay for me to write a book on biology, but I'm not qualified to be writing a popular book about military technologies. And I started very gently looking into this. And then I started coming across some of these military scholars who'd also been looking at the parallels and realizing that all these ideas lined up. And it started little at first. And again, one more caveat here. I was brought up in a generation where we were trained pretty strictly. There's a line in the sand. I mean, there's biological evolution on this side, and there's cultural evolution on that side. And they're only kind of superficially similar. They're not the same. And so that's kind of the mindset that I brought to it. So when I started trying to do this, I was going to have all the biology stuff, and then I was going to have a transition chapter sort of explaining the logic and how similar these are, but why they're not quite the same, and then get into the military. And then my editor's like, no way, man, bring the military stuff into the beginning. There's no way you can wait till the end. So then I'd have a chapter on biology with a box. It's like I physically separated it. So it's like separate. Here's the biology, and then here's the parallel. And I was just going to sprinkle these parallels in. And then at the end, I was going to have the transition and explain the difference between biological and cultural evolution. And then finally, they're like, no, just go back and forth. And in the end, half the book ended up being on military stuff. So for me, intellectually, I had to come at it gradually. But also, I decided that there is no difference between cultural and biological evolution. I think I was raised in a mindset that is wrong. It's outdated. Initially, it was all based on this idea that DNA is sort of longitudinally transmitted, and that's sort of true biological evolution. And that's why we get such a clean sort of phylogenetic signal. And cultural characteristics can also be passed down. So you get a little bit of a signal. You can build a phylogeny for languages or pottery technologies, but there's a lot of horizontal transfer and a lot of sort of stealing of ideas and teaching. And because of all that sort of horizontal bleeding of information, it's not quite the same. But I think that you all would agree now that with all that we're learning, particularly about microbial evolution, but also the more we sequence genomes, the more we realize that pieces of genomes are being introgressed left and right all the time. I think there's a ton of horizontal transfer even within traditional biological systems. And this sort of distinction that for many, many, many years was ingrained in us is just flat out wrong. So yes, I think it's okay to go back and forth. I do now think the parallels are really striking and they're really obvious, but I got to be fair and say it took me several years to get there. It's obvious in hindsight, but at the time, it was actually a harder leap than you might think, if that makes any sense.
Yeah, but yes, definitely. Thank you.
Sure.
Our next question is from Leticia Aviles.
Hi, Doc. That was a lot of fun.
Hi, I didn't see you before. Good to see you.
Yeah, I'm somewhere in there. Yeah, so for people who may not know me, I'm at the University of British Columbia, and I work on social spiders. And I'm just curious, after an arms race falls apart, what comes next? and both in animals, and what would that mean for human, and what has happened through human history, I guess, and what do you think might happen now?
I think it's an awesome question. And I think that the sort of default assumption a lot of us tend to make when we think about this is that the lineage goes extinct. And there are these charismatic cases like the Irish elk, where, you know, way back when Gould even argued that this sort of selection pushed them over the brink to the point where they went extinct. And then there's some really beautiful, more recent modeling studies where they looked at climate changes in forage, and they figured out what the energetic costs would have been. And there really is an almost compelling case that in the situations like the Irish elk, the weapons might have driven them extinct. But I think that's exceedingly rare. I think what happens much more often is they just get rid of the weapons. I can use the beetles that I used to work on, for example, the dung beetles. They already have a switch mechanism built in that lets them turn off weapon growth. Females never produce the weapons in most of these species, not all, but most of these species. And in lots of these species, the sneak tactics have arisen, and the small males dispense with weapon growth too. So facultatively, they've already got the capacity to turn the weapons on or weapons off. So if you reach a tipping point where they're just not cost effective anymore, it's easy to just ditch the weapons. And we used to see this with the phylogeny. You'd map the weapons onto a phylogeny, and we'd see gain, loss, gain, loss, gain, loss. I mean, at first you have to kind of scratch your head and say, did we really map these characters correctly? I mean, they're supposed to be better and bigger, and you expect these things to not disappear all the time. And yet we'd find as many instances where the weapons were lost as where they were gained. And now in hindsight, I think that's what's going on. I think this is a system that's sort of wired for arms races, and the arms race goes off in a lineage and the weapons get huge and then they disappear. And then, you know, a while later, the system is still poised and ready. A different bump or a different knob pops up and they go off on a different trajectory. And now you got a different kind of weapon. And I think that this kind of a cyclical process can explain why we see such stochastic and otherwise superficially random variation among species in the types of weapons, and why there are so many gains and losses. It's a hard thing to test. So I don't think we've actually tested that satisfactorily, but at the moment, at least, the patterns fit with that kind of an idea. So it's a long-winded answer, but I'm essentially saying when they're not cost effective, they just stop producing the weapon. It's not like they go extinct. They just stop producing the weapon, but all the rest of the biology of those animals is still there. So the conditions are still there. So that system is essentially poised and ready for another trajectory or a different kind of weapon.
So the one question I'm wondering though is, without the weapons, then how are conflicts resolved, and what made that mean to, you know, human situations?
Oh, sorry, you asked about the human situation.
Well, no, I know, but also like, how do conflicts resolve without the weapons then? So it's a kind of a free for all, everything goes, or?
I mean, I'm going to revert back to beetles, which are the ones that I spent most of my life thinking about. I mean, I think in the beetles, the species without weapons still fight too. They fight all the time, and other things in some species, things like agility might matter, but I think a lot of times just the bigger males do better. So I think they would still fight, but I think then that system would be poised. So if in that lineage, another bump rose up or another type of a weapon started to appear, then those males would have an edge, and it would very quickly seep through that population. So I think they would still fight battles. And I think that bigger males would probably, or better conditioned males would still win. But I'm predicting that down the road, another weapon would pop up and they would start on a different arms race. You asked about people, human situations. The military does a fantastic job at documenting this. This is one of the weaker parts of biology. I mean, the fun about going back and forth is there's some things that the military history tells us really clearly, and they don't have any information about others. And then in biology and behavior, there's some things that biology teaches us, but we have sort of gaps too. And so one of the areas where biology is really limited, there aren't that many cases where we've watched an arms race collapse. In fact, I'm not sure I've seen any really good examples where we watch this phenomenon happen and we actually watch the weapons disappear. But the military has loads of examples of this. Essentially, every single arms race through the history has always collapsed at some point, and they know exactly why it collapsed. So it was really one of those areas where the military history shines, and it's always these new cheating technologies or these things that break the rules. So what happens is then the countries or the nation states stop producing the extravagant weapons because they're not cost effective anymore. But it doesn't mean that other arms races won't pop up at other places on the landscape. They still have conflicts. They're just not, it's not cost effective to invest in those types of extreme weapons. And in some cases, the sneak strategies just get folded into the arsenal. I mentioned this in the chat, but submarines brought down the battleship systems, but all navies have submarines now. So they've still got, you know, full fleets of navies, but they've now incorporated submarines into the suite. They've got the huge carriers, but they've also got the cruisers and the destroyers and the submarines. All of these sort of faster, more agile, mobile ships, they all have their sort of specialized niche, and they're all sort of folded into the Navy or into the arsenal. So sorry if that was a little off
That's
topic.
great.
Thank you. So for those of you who have never said hi, please don't be shy, and we'll take you if this is the first time that you want to ask a question or introduce yourself. The next question is going to be from one of our regulars. Eleanor, please go ahead.
Hi, I'm Eleanor from the University of Derby in my second year, and I thought your talk was really great. I really enjoyed it from a student perspective, so I know why your students enjoyed it. But you sort of commented on this already, just answering the past question, but I was wondering how, obviously you've talked about male-male competition, how much it is seen in female competition, maybe where there's high competition for mating resources like breeding spaces. Is it seen in females? Is it like weapon evolution, and or is it sort of like not cost and benefit sort of? I just wanted to know how much it is seen in females from all your research.
It is seen in females. It's nowhere near as common as it is in males. And probably that falls back on the sort of first principles of sexual selection and parental investment. And it's just that the price tag with these big weapons is less likely to be justifiable to females than it is to males. But you do still see systems where females fight with rival females. And there are fun examples of systems where females do produce the weapons. So within the cervix, the poster child or the caribou, where females in some populations, but not all, have mini versions of the antlers, which they use to fight over critical winter resources that they need for their young. We see a lot of the dung beetles where females have weapons, a surprising number of them. In some cases, it's a relatively smaller version. And we don't yet know whether it's kind of baggage that's carried along for the ride because of genetic correlations that haven't completely broken down yet, or whether the females are really using those weapons. And maybe they're a little bit smaller, again, because the trade-offs and the price they pay is a little bit steeper. So their cost-benefit balance point is a little bit smaller than the males. A lot of those species haven't been studied well enough for us to really look at it. There's one cool species that we got very involved with looking at where the females produce the big weapons and the males don't. And that was super cool from a developmental or a mechanistic standpoint. And it's something that Armin Mochik at Indiana has dug in even deeper than we did. And in those situations, the females really are fighting over limited resources. They'll sneak into the tunnels and steal the dung from other females. And we think that the weapons are, presumably weapons are limiting, presumably resources are limiting enough in the field that it warrants the investment in the weapons for the females. Unfortunately, we've only been able to study them in the lab because the native range for this Onthophagus sagittarius species is the India-Pakistani borderlands. It's not the safest place to do field work. So we only know what we know from the lab, and I admit that the conditions in the lab are at best a proxy. But anyway, yes, you see systems where females have weapons, and they're very cool systems, both mechanistically and behaviorally, but they're relatively rare.
Okay, thank you. That's great. Thanks.
Sure.
Our next question is from Clara Grethen. If you would like to introduce yourself, Clara.
Hi, I'm Clara. I'm a PhD student at the University of Bern. Thank you so much for the nice talk. I really enjoyed especially the audio. It was so nice to hear some good audio. One tiny feedback from my side as someone who's not native in English, I found it a bit fast. It was due to the quick cutting and also the it's more rehearsed if it's a video, of course, because you have the time and stuff like that. So I don't know if that's because of the language or if anybody else felt that way, but for me it was just it seemed a bit fast to follow.
Go ahead.
Yeah, sorry. For my question, it was because you had just said that the arms race is you never saw one escalate in that way.
We never seen one collapse.
Yeah, sorry, that was the word.
I don't think we've ever seen one collapse.
Yeah, and I was just wondering then, transferring it back onto military arms races, and in cases like something like a huge escalation like the Cold War, and this takes us a bit away from biology, but maybe we
Okay,
can
no, I
learn
said
something from
anything goes. It's all
biology.
good.
Yeah. So, what does that tell us then? Transferring back to biology and escalation of such conflict, if we've never seen something like the Cold War, these long arms races that kind of end in a complete collapse or I don't know how else to better put it.
Mhm.
Do you know what I'm trying to get at?
Yeah, I mean, I think there's parallels at lots of levels. So it comes down to which aspects of the Cold War you're trying to make the comparison with. So for example, one aspect of the Cold War that I think parallels very nicely what we see in animal populations is that the arms race during the Cold War happened on many, many different fronts. So there was an arms race with submarine technologies. There was an arms race with tank technologies. There was an arms race with ballistic missile technologies. All of the technologies were sort of involved in an escalation at the same time. And I see that as very analogous to the evolution of multiple signals in animal systems where, females might prefer a male that not only has a big tail, but also has a color patch and also does a dance and also has a song. The multimodal signaling and the sort of piling on of one costly trait on top of another, that is actually very parallel to the kind of thing that we saw during the Cold War. I'll make another parallel too. The Cold War was predictable in the sense that it was sort of a one-on-one fight, and the two sort of superpowers went off head to head, and things started to heat up. They started to escalate several times. So the proxy wars, as they're called, Afghanistan, Vietnam, Korea, all these things were confrontations that very quickly aligned between the two superpowers, and they started to escalate, but then they didn't go nuclear. They involved a lot of conventional weapons, and a lot of people did die. So I'm not going to belittle the price that was paid. But the fact is, those were confrontations that started to heat up. It's just like two bucks sparring a little bit, pushing, oh yeah, they're still there, back down again. And the very fact that none of those went nuclear, I think, is evidence for the predictability and the assessment component of these types of one-on-one interactions. And that gives me hope that a duel, at least, is something that can de-escalate. The situations that really scare me right now are scrambles, because in scrambles, as far as I can tell, there's no opportunity to assess a rival. You just go in with everything you got. And those are, if you start having multiple nations all battling and they have weapons of mass destruction, that kind of a political dynamic, I think, could be way less predictable, a lot harder to anticipate and a lot harder to deal with or to step back down from than something like what happened during the Cold War. But the last piece is the weapons of mass destruction component. There really isn't a biological equivalent of weapons on that scale that I've been able to come up with. And I've struggled with it a lot, because in my book, I kind of came to a pretty depressing, scary conclusion. If you use the biology of expensive weapons like tusks or antlers or horns, and you look at the world around us, we're basically screwed, because conventional weapons still play by those rules. Aircraft carriers and F-35, these things are tremendously expensive, honest signals, but the nuclear weapons aren't. There's like 9,500 of them still out there. They're not particularly expensive. Anybody could have them in principle. The things that can really wipe us off the planet aren't actually playing by the same rules. They're not costly, extravagant things like tusks or horns. And so there should be no deterrence. They don't meet the requirements of a deterrent. And yet these things sort of are. So I don't know, I've been struggling. I've been looking to things like chemical weapons and coral snakes and starting to think of whether there's biological precedents for weapons that aren't hyper variable. They're not super costly. They're not a signal of individual variation. They're just there, and they're so bad you don't mess with them. And whether something like that is a better analogy. But I think there's a lot of lessons to come out of the Cold War. It's just, it was a scary, scary time, but also interesting on lots of levels. Does that get at what you're asking?
Yeah, it does.
Oh, and one of the
if I make, yeah, sure.
On the talking fast, it's also on me.
Okay.
I get really excited and I tend to go, I mean, my student evaluations at the end of the semester say things like breathe because I just go. And so part of that's on me. And I guess what I could try to do if I do this again is have it captioned so that if English is a second language, then maybe there's that also. I apologize if it was too quick.
It's okay. If I may continue with a direct follow-up on that.
Can we have lots of, can I
Okay,
ask Clara
sorry,
to
yeah,
wait?
sure.
We have lots of questions. I want to give everyone a chance. So
Of
remind
course.
me or type your question mark again right now. If
Yes,
we
I
have time,
will.
we'll take a second question. The
I
next
will.
question is from Carolina.
I can't see all the hands up. Does that mean I need to do a quicker job? Try to give
Oh,
shorter?
no, we are. Carolina,
Yeah, I'm
Pacheco?
here. Can you hear me?
Oh,
Yeah.
yes, we can hear you.
So hi, I'm Carolina. I'm a graduate student from the University of Porto, Portugal. And amazing presentation. I absolutely love it. I will just ask you one question, and it's about the parallel with the deterrence aspect of the weapons. So one thing that you mentioned is, for instance, for Alpha, sorry, and now I forgot that you have the biggest weapons, but they are very peaceful. So, and the immediately thought was, would that have an impact on the ecological fear around the landscape? And would that influence the population structure or actually their genetic variability within that population, as it could be manipulated toward the ones that have bigger horns or bigger weapons? Do you have any thoughts on that?
Okay, I may not have a very satisfying answer here. You're asking, I mean, first of all, this idea that so many of these conflicts are resolved without a fight really kind of caught us off guard too. And I'd spent a lot of years, and I'm looking at Umat's picture here too. I know he's looked at fights between animals a bunch. You know, we tend to only count the fight when they really fight. So if you look at a field study and you're looking at who wins what percentage of the fights, if the males kind of look at each other and one walks away, I mean, historically, I wouldn't even count that. It's like, oh, that wasn't really an interaction. And what this frame shift in my worldview has done is it's caused me to go back and look at systems like my own and say, whoa, wait a minute, that counts. That could have been a fight, and it wasn't a fight because it ended before it began. And there are relatively few studies of agonistic interactions in the wild that I think really include the full spectrum of male-male confrontations, including the 90% that don't go anywhere. And so part of the reason that number seems so shocking is that we really only tend to focus on the fights. So we're only looking at a subset of the interactions when we look at the effective weapons or something like that in the wild. So this deterrence function, I think, is real. I think it's something that's been out there, but we just haven't looked at, or I at least wasn't looking at these populations from the right vantage, if you will. I had to learn how to see them differently in order to notice that pattern. I don't know. I'm not a population ecologist. I don't really understand what it would mean in terms of numbers of individuals. I still think that reproductive success can be just as skewed in these populations. It's not that the biggest males aren't still monopolizing access to reproduction. So in terms of what it means for genetic variation, probably not much. You still have a very small subset of the males monopolizing access to the breeding. It's just that it's not a bloodbath because the males are sort of sorting it out amongst themselves on the landscape without escalating into the costly battles as often. So calling it peace, I know it's provocative and it makes everybody mad, but the fact is, you know, if you've got a system with these huge weapons and you use this more inclusive way of including these interactions as confrontations and 90-something% of them never fight, what are you going to call it? I mean, it's definitely not as much of a battleground as you would think it would be, just walking in and, you know, characterizing that species by the monstrous weapons. So it's a lame answer because I really haven't thought about what it would mean for the ways that species interacts with other species or with population structure. But that's my first pass at it.
Thank you.
And I don't mind being wrong, by the way, I'm used to it. So if people disagree with this and you think I'm looking at these interactions in the field wrong, tell me by all means.
No, I was just thinking about the movement within the species or between populations, because that kind of interaction could affect movement without us noticing. That was what I was thinking, if you had any idea.
Okay. I don't know. I mean, I think when I think of these things, I think of things like fiddler crabs. And situations where they might, a male will guard and guard and guard, but eventually they run out of food and they have to abandon and they have to go down to the beach and they give up their territory. Instantly, it's taken over by another male. They go feed and then they got to work their way back up the beach. And it's like hundreds and hundreds of these crabs all waving. And, they don't fight with every male they approach. They kind of size each other up. And it's a very non-random path that these males take before they end up challenging somebody that they have a chance of actually beating. It does affect their movement in a way, but I'm thinking of how they move through the minefield of rivals on a beach, not dispersal among populations. Again, it's all, I admit it's a relatively new idea for me to be wrapping my head around. So.
Thank you. Our next question is from Andrew Gersick. Andrew, if you would like to introduce yourself.
Hey, Eduardo.
How you doing?
Okay, I haven't seen you in a while. I'm Andy Gersick. For those I don't know, I'm a researcher in EEB at Princeton. I study social communication and behavior.
Awesome.
Some zebras, some hyenas, some different animals.
I'm partial to Princeton. It's been a while though.
It's a nice place to be. So I was thinking about your poster and the sort of that's relatively small, as you pointed out, sort of number of species, but also a small number based on the boundary you've drawn around what constitutes a weapon. And so I was thinking, like, what makes it onto that poster or doesn't? What is a weapon or is not? Is venom a weapon? Is a spitting cobra using a weapon? And then even beyond that, I was thinking about like the martial arts master whose greatest weapon is her fist, and whether behavior that has to be invested in and that has a particular aggressive or defensive value constitutes a weapon. I mean, it certainly can in terms of its effect. And then you focus your discussion on these material structures that are costly to build. Do the dynamics play out any differently if you allow behaviors to be weapons? Are they truly out of your study set and out of this model, or are they in the model?
Well, I get you on all fronts, and absolutely behaviors. So first of all, these sound easy. They're not. Like, what is a weapon? I wrote a book on animal weapons. You'd think I would have like the world's quickest draw on that answer, and I don't. Absolutely, chemical weapons are weapons. In my own case, I had to sort of confront the fact that I couldn't be an expert on all these things. I had to focus. I like the extremes. I mean, I don't have a good rationale for it. I'm obsessed with the extremes, these things that look like they shouldn't be possible. That's where I've spent my whole career trying to dig in. And so when I was writing this book and really trying to survey across systems, I had to draw some lines. And I took the chemical weapons off the table pretty early on. I had a long footnote explaining that these are great sources if you want to learn more, but it was pretty apparent to me right out of the gates that they didn't play by the same rules. So if I was trying to sort of distill down the essence of these weapons, the lessons I was learning for tusks or horns or antlers didn't necessarily apply to the chemical weapons. And so rather than pretend they weren't weapons, I just said, I'm only going to focus on these. Mm-hmm. But it gets to the next piece. I was really focusing on the big stuff, the extremes. So here, you'd think defining a weapon would be easy. It's not. So in my book, I ended up talking about defensive weapons as well as offensive weapons. And I would consider the Kevlar and the camouflage and the things, the night vision goggles that our troops take into combat. Those are weapons too. They're helping aid the performance of our soldiers in combat. And there's a lot of parallels between armor and spines and defensive characteristics of military weapons and animal weapons too. So of course, those are also weapons. So I kind of focused on the big stuff, but even there, it's not easy. What's an exaggerated weapon? When I was working with a grad student, Devin O'Brien, and he was trying to summarize these things, and we were trying to write sort of a review on this, and it's like, we came up empty. Umat knows this. He was involved. We couldn't do it. We tried to define what is an extreme weapon. We did it in terms of parallels with sister species. We did it with comparisons to other body parts in the same animal. It's not easy. It's one of those things like, it when you see it, but actually drawing the line in this, is it 20% of your, where do you draw the line? We gave up. It's like, whatever we do is going to be completely arbitrary. And so we avoided it. So I'm coming up empty on all of the aspects of your question, Andrew. Well, one more caveat. I tend to focus on the big stuff. And I do think that there is a suite of biological characteristics that goes hand in hand with a very important subset of the big stuff. And these are the weapons that function as honest signals that convey information about among individual variation in quality of some sort. And again, quality is another thing that's awful to define. I work at the intersection of all these impossible to define things, but really big, costly traits are informative as signals as such. And so one of the fun things we started to do is look at other extreme weapons that don't function as signals, or other extreme structures like Jerboa hind legs, big exaggerated things that aren't used as a signal. And it turns out they're very different. The characteristics of these traits are very different. And the big weapons have huge amounts of among individual variation. They're hyper variable. The other kinds of exaggerated traits like Jerboa hind legs are not. So steep scaling relationship or not steep scaling relationship. One set is exquisitely sensitive to nutrition and condition, so extra sensitive. Other traits are not. So there really is sort of a package of characteristics that goes with this class of weapons that I focus on. But man, it's not a very satisfying definition, and I apologize. So I see you not nodding.
Apology not accepted.
Okay.
No, it's great.
Thank you, Andrew. Our next question is from Umat Somji.
Okay.
Umat, if you can introduce yourself.
Great.
And then you can take a stab at answering Andrew's question. I'll put you on the spot.
Hi, so my name is Umat. I'm a postdoctoral researcher at the Smithsonian Tropical Institute in Panama. And a lot of my work actually is on looking at animal weapons, particularly in this group of insects called the choroids. I'm actually like the academic grandson probably of Doug, because his student was my professor during my PhD. So my question for you, Doug, is
wait, you're not going to take a stab at defining a weapon?
Well, okay, so I've recently thought a little bit about this when it comes to what a weapon is, and I thought that, you know, for sure that we can try to, I mean, it's really fascinating that these weapons occur in marine isopods and in elk and in prehistoric elephants and in all these different groups, but they're often very common in these specific groups, and they evolve very rapidly in those specific groups, and they're absent for most of them. And, you know, for example, like, you know, in birds, and Doug, we know, you know this, birds often don't have really big exaggerated weapons. Even for some of the most iconic sexually selected traits, for example, like the big trains in peacocks, if you actually measure the mass of those traits, they're only about 6.9% of body mass. And so they're really large, and recent studies have shown we can't even detect decreases in performance with peacocks with tails than those without ones. And so sometimes it seems like they're not as costly as it might imply just based on their size alone. And then you get something like the eastern kingbird, a male in that species, likely does these behaviors where it does these big somersault behaviors during flight. And males in that species invest about 30% more in muscle mass, in breast muscles, compared to females. So in you know, Darwin has that famous saying, you know, the thought of a peacock's tail makes me sick. This is like a little bit of anti-nausea for him, because maybe the thought of eastern kingbird's muscles that are 30% of body mass, you know, would be something that's more striking. But they're cryptic to us because, you know, we're not looking at the physiology in that way. We are attracted to these bright and colorful traits. So I think that energetics might be a good way, and that, you know, to kind of think about a similar kind of cost of these traits in different organisms. And it might be that a lot of like sexually selected traits are like keratin, bone, feathers, you know, they're often composed of non-metabolically active tissues. So they're not draining resources all the time.
I'm going to add a twist, and then you can come back to your question, but I like that stab at it. And by that stab, Andrew, coming back to your question, those enlarged muscles, because they're used in agonistic behaviors among rivals, I would consider that to be part of a weapon system. But the cost is even tricky too. We learned this one the hard way, because looking at our own beetles, the weapons are way less expensive than we would have predicted. And I now think what happens is initially when these structures get big, they're very expensive. But that selects for individuals that are able to stumble on a way to produce a really big structure at a slightly lower cost. And so I expect that these weapons over time become less costly as organisms figure out how to produce them with less of an investment. And of course, that undermines their efficacy as a signal. And at some point, that probably leads to the origin of another signal or a different system that is still costly. But you can go into populations and see these things that you expect or you assume are going to be massively expensive. And they might not be, because they've been out there long enough that organisms have stumbled on ways to ameliorate those costs. So even simply using the cost as your definitional line in the sand isn't necessarily perfect, depending on where in the arms race you're at. All right, Uma, what was your question?
So my question is about allometry. So we know that in many weapons, larger individuals produce disproportionately larger traits. And I was wondering if first a lot of the mechanisms that you talked about, the scramble and doors and stuff, those are like within species processes. Sometimes we often see positive allometry across species. So, what is the process that leads to different species investing in disproportionately large weapons? And do you see like similar allometric scaling patterns in human societies and the cultural evolution of weapons?
So what would you look at for an allometric scaling relationship in cultural evolution? Like, I mean,
the size of a country and its relative investment in armies or something like that.
Interesting. I'm going to punt on that one because I really haven't thought. I know that there are general trends that nation states invest as much as they can. It comes down to this idea of discretionary resources. There's a certain fixed amount you pretty much better spend on infrastructure and public health and things you need to stay alive. And then countries differ spectacularly in the pool of discretionary resources they have above and beyond. And that does, on average, predict investment in military pretty well. But there's exceptions. There's places like Costa Rica, for example, that just don't produce militaries. And so it would definitely be a graph with a lot of scatter. But oh shoot, the first part about
like these are within species patterns. What might explain these across species? I
think we're thinking about this a lot because the beetles that we work on, even within the species, if you look across the range, if you look population to population, they differ in the relative size of the weapons. And we've been starting to do a lot more field work and trying to measure selection on these traits in the wild to see if we can figure out what's driving those among population differences. And honestly, I mean, we definitely find some places where the mating system is way more predictable, very limited territory abundance, intense competition for a small number of territories. It works very cleanly and the males with the biggest weapons win. Those are also the populations with the really long horns. Other places where it devolves, the territories are more, the feeding sites are more abundant. The chances that a female would visit any particular one are lower. So the benefits to cost shift. They have a lot more scrambles. We're starting to look at whether the fights are consistently duels in some places and duels plus a certain amount of chaos devolving into scrambles at others. It's something we never looked at before, but it may be that in this population, 95% of the fights are all duels. And so the payoffs to weapons are awesome and consistent. And over here, it might be only 80% of the fights are duels. And that means that even though those fights still are won by the big weapons, there's 20% of the conflicts are more stochastic and the weapons aren't helping you. And the net effect might shift that balance and lead to slightly weaker selection on the weapon. We don't know. So if that kind of a process could start to drive weapon size differences among populations, then that's my best guess for how would you account for differences among species is just iterate that over time. You're going to get local ecological differences in those costs and benefits that sort of set the point where the arms race stops.
Thanks.
Thank you. I'm gonna skip Magen. I'm sure you'll understand. I wanna let people we've never heard from them go first. So Federico Reyes from Uruguay, if you're there, you're welcome. If you wanna introduce yourself and ask your question.
Wow, all over the world. This is pretty amazing.
Hi, thank you. Thank you
Nice
for
to meet you.
Thank you for the opportunity to introduce myself. I'm Federico from. I'm a PhD student from Universidad de la República in Montevideo, Uruguay. Are you listening? Okay, the audio is okay.
Yes.
I work in. I'm studying aggression on actually hormonal basis of aggression in animal fishes. Maybe you heard about. We have a lot of species in Uruguay, endemic from Uruguay. We are studying natural populations, but we also study dyadic encounters.
Which species are you?
Australebias. The genera is Australebias.
Okay.
I can write it here.
No, that's all right. I just didn't hear what, I'm just trying to picture the animals. What kind of animals are they?
They are cyprinodontiforms, animal fishes, or maybe they are more known as killifishes.
Okay, got it. Thank you.
For example, Notobranchius in Africa is also an animal fish. These fishes have a very short cycle. Just as a very short introduction, they live in temporary ponds that dry out in the summer. So they have a very rush life. They mature. They have a sexual maturation in very few weeks, and they only have one reproductive season. So the first question, we are studying actually the assessment strategy in this species. I have read that maybe in species that have a single season or a single brood, no assessment would be expected. What do you think about that expectation? But these species have a unique particularity that is a single season, but it's a long season. So I don't feel very comfortable with the prediction that we will not see any kind of assessment strategy in this species. What do you feel about that?
I guess I'm curious why the fact that it is essentially an annual is considered relevant to whether or not they assess. I mean, my sense is it would come down to the population size and the extent to which resources are monopolizable. I mean, I think of something like a mayfly, where they're coming out in massive swarms for like 2 days and then dying. Yeah, it's a scramble. There's probably no real room for assessment, and there's really nothing that you could fight over or defend anyway. But I mean, the beetles we work on are annuals. They have 1 generation per year. It all happens in a big burst in a couple months, but that's still long enough for these beetles to really fight it out. And the resources are still limiting enough that you get intense battles over access to those resources. So unless I'm missing something, sorry about all the clanking, by the way. I think I mentioned in the chat that my roof is leaking into a bucket and they're banging around fixing something outside my door. But I guess what I'm saying is the fact that they have 1 breeding season per year isn't a reason to assume that they're not assessing each other. Assessment, I would predict, would come down to the nature of the competitions that are occurring, who's fighting with who, what are the resources they're fighting over, and is there any way to predictably assess ahead of time whether a male is likely to lose a particular fight. I mean, that's really what assessment is, right? It's a way that a male can decide ahead of time that it's probably not worth escalating because they're probably not going to win. And that's a situation in some cases where it pays that male to go look for a different battle. So the question is, do you get those kinds of interactions happening? And if you do, then of course I would expect them to be assessing.
Great. Great, thank you. And if I'm allowed, given that you did a lot of parallelism between animals and humans, I would like to ask you about a terminal investment strategy, which also we believe we have this situation in animal fishes. They are expected to invest more in aggression in reproduction. We actually have we just published a paper in Animal Behavior regarding the effect of cortisol, and stress in reproductive performance. I'm now studying the same protocol, but in aggression. How the cortisol, how the stress influence aggression on the light that in the light that cortisol, we have seen that it rises till the end of the season. So these temporary bonds start losing in conditions are getting worse till the end of the season. So cortisol rises till the end of the season. We believe it would be room for a terminal investment. And the question would be, have you ever looked or explored a terminal investment in countries, in human societies? That, for example, a government or a country whose government is very likely to finish, an empire who's about to finish, that they became more aggressive or more, yes, that's the question.
I have never thought about that. So I actually am drawing a complete blank, but I'm curious if anybody else on the Zoom can think of, I mean, I can certainly think of examples where empires were collapsing or governmental systems were collapsing, but whether they recognized that at the time or not, or whether it's only the perspective of hindsight that let us see that they were collapsing, I don't know. I don't have a good example for you, but I'm kind of dying to know if anybody else on the Zoom does.
We need to be respectful. I really want to get to the people who ask. So if that's okay, we have some young colleagues they've never introduced themselves. So really want to take. So we have next Tom. I apologize. I'm going to try to pronounce your name. Tom Tandaso Canil. Please, if you would like to introduce yourself and ask the question.
Hello, thank you very much firstly for that wonderful talk. I am Nom Tandazo. I'm a PhD student at the University of Mainz. So my question, I think you might have touched on a little, but I was interested in the nutritional investment really that these beetles have to make, or these animals have to make in building these very, very large defensive structures. And I was wondering if you know, maybe if they have additional relationships maybe with microbial partners that might help them to provide some nutrients that may be essential in building these structures. I mean, with human warfare, you know that the amount of investment that's needed is in terms of resources that are financial, material, but what do you know in terms of the animals?
All right, awesome question. And you took me on a twist. I was all set to answer it until you asked about the microbial communities. So quick answer, a lot of the systems do depend on microbial communities, including many of the beetles. They would not be able to process or eat the diets that they eat without gut microbiomes and symbiotic relationships. But I'm just going to set that aside because I don't know a whole lot about it. I do know a lot about nutrition. I spent a lot of years looking at the link between access to nutrition and growth in the beetles, trying specifically to figure out what's so special about the weapons that causes them to be more sensitive to nutrition than other body parts. And the quick answer, because I can see people squirming and I think I'm going to run out of time in a couple minutes, the really quick answer that took us like 15 years to get there is that in many of these systems, we think that the cells in the weapons, in the exaggerated structures, are extra sensitive to the insulin signaling pathway. So either the insulins per se, or insulin-like growth factors. In a sense, if you think of a beetle, it's like a big sack, and they've got clusters of cells that are making the legs and clusters of cells that are going to make the genitalia, make the wings. All the adult structures start as sort of clusters of cells, but the ones that are going to make the horns are extra sensitive to these nutritional and physiological signals like insulin. And that means that very subtle differences in the constitutive levels of these hormones in these animals make everything a little bit bigger, a little bit smaller. So all the legs, the wings, the genitalia, all those structures get a bit bigger when the animals are well fed and growing larger, and a little bit smaller when the animals are poorly fed. But the weapons, it's like dialing up the volume. So if the insulin levels go up, the weapons get huge. And if the insulin levels go down, the weapons get tiny. And so by being hypersensitive to this ancient metazoan physiological pathway, they're essentially dialed into overall physiological condition. And it's a beautiful central clearinghouse mechanism, because interactions, if you lose fights, those kinds of social interactions can drop your insulin levels. If you're infected by parasites or pathogens, insulin levels drop. It's this sort of central clearinghouse gateway physiological system that dials in nutrition, dominance interactions, health, all the things that matter to determine the instantaneous physiological state of that animal are reflected in those hormone levels. So I do think they're exquisitely sensitive to nutrition. I think the weapons are hypersensitive. There's evidence in antlers and cervids, there's evidence in crabs, there's evidence in birdsong and all these exaggerated structures that have been looked at, most of them are extra sensitive to insulin. Not all. In fact, even the stag beetles, one of the systems we worked on, are not, but a lot of them are. But how the microbial communities fit in is still wide open. Sorry. Cool.
Thank you very much. Thanks.
Doug, I'm going to ask for your patience. We have our last final question from Mina. I apologize to those of you who are not calling. It's because you've asked questions in the past and we're already running late. Doug has to go teach. So I'm arbitrarily giving the last question to somebody that we haven't heard from. Mina Kanani Davidson, please go with your question. Doug, and then thank you so much. So we'll let you run after this question to your teaching.
I'm cutting it close, but this is fun. So thanks, everybody.
Hi, thanks for taking my very last question and great talk. My name is Maina. I'm a PhD student at the University of Michigan. And I hope this isn't kind of too tangential of a question, but I'm curious, like, for some species, it seems like they have these honest signals of male-male competition where they are kind of having these duels, but the signal isn't exactly the weapon itself. And so I'm curious, like, how this kind of plays into your system, whether it might be something where they would have like invested in a signal previously and then somehow shifted over to a signal with the fitness trade-offs, or just your thoughts on that. Thank you.
Bina, I just have to laugh because you just put your finger on everything that we're currently doing in my lab right now. I mean, you know, part of the fun of having been in biology for a while is we can look back on our past career and laugh at all of our mistakes. Most of the things I've gotten excited about in the past have all turned out to be wrong. The irony here is that I spent 15 years, this gets back to, I don't know how to pronounce your name, Nam Tandans. The previous question, I'm sorry for not pronouncing your name right, about nutrition. I'd spent all this time looking at the physiological mechanisms that make a structure like a rhinoceros beetle horn an honest, sort of unfakeable signal of the condition or the quality of the animals. And then we discovered that in our own rhinoceros beetle, the main species we work on, they don't use the weapons as a signal at all. I mean, that's kind of embarrassing. It's like I just pitched my career on these kinds of things being signals. And I think in general, they really are. But we kind of came up against the reality that in our own beetles, they're not using the horns as a signal. And instead, they're using all these other signal modalities. So the males fight, and then they get hold of a territory. And then that's not good enough. The females come in to feed and they reject most of the males. So the males will climb onto the back and they'll start stridulating and singing these songs, and they do these vibrating dances. And we think they have real-time blends of cuticular hydrocarbon chemicals in their waxy cuticle. All of these other signal modalities appear to be communicating something that the weapons just aren't. And that's our big question right now. What are they getting? Why are they ignoring the horns? And what are they getting from these other signals that they couldn't get simply by looking at the horn? So we have all these sound boxes set up, and we're trying to do field work, and the field work all got canceled because of COVID, but we're going to pick it up next summer. We're starting to try to look at these other signals and look at the females. What are the females paying attention to? And also look at the males during the fights. What are males using as the real-time signal when they assess each other? I mean, I know I just built my whole research story around the weapons being the signal, but you know, what if it's not? What if they're using one of these other signals or a combination of these other signals? Which ones are they using and what information are they getting? Literally, that's the question keeping me awake at night right now. And all I can say is maybe I'll see you in 2 or 3 years and I'll have a good answer for you.
Thank you.
Thank you.
Thank you very much, Doug. We'll let you go to your students, who I'm sure cannot wait for you to engage them as vividly as you've done with us. So thank you so much. And thanks to all of you. Like I said, I mean, you know, we're seeing each other again on next Tuesday when Sean Strassman will present her talk. So looking forward to seeing you all in a week. Sorry to those of you who didn't get to ask your questions. I'm sorry. Fede, un gusto conocerte.
Eduardo, don't forget to end the live stream.